This video is talking about using a rational function to describe the relationship between time and the number of fish that are recovering. It's a certain species that the government is trying to improve their habitat and restricting fishing in order to bring back a population. And the reason why a rational function fits this particular problem is that there's some limit at which they believe the population won't be able to go above no matter how much they do. For example, you might have deer in an area. There's some limitation. The vegetation and predators are going to go ahead and keep the population at a certain limit. And so we're going to see that that will turn out to be some kind of a horizontal asymptote that the growth of the population will reach and not exceed. But let's just walk through all the steps of the problem. So it says here, what is the population of the fish at the beginning? Well, that is really our, when time is zero, we're going to have some kind of a beginning population, which is going to be our y-intercept. So as you always do with finding y-intercepts, is you let x, or in this case t, be 0. So we're just going to go ahead and evaluate the function at 0. So the number of fish at time 0 is just going to be 20. And I'm just using the function right here. Right? It's just going to be 20 times 4 plus 3 times 0 all over 1 plus 0.05 times 0, right? And a bunch of those terms are going to eliminate, and we're going to end up with just 20 times 4. This will go to 0. This is going to go to 0, so we'll just end up with 80 over 1, or 80 is the number of fish at the beginning. In fact, we could go ahead and plot that down here. We're going to also do a graph of our results. And so let me just take a look. It looks like this is skipping by 100s, 100, 200, 300, 400. So 80 would be our y-intercept, somewhere around there roughly. Okay, and then the next one is find the population after 10 years. And this is nothing more than evaluating the function at 10. I'm not going to do all the math here. I'll just show the answer, but this would be the setup. Okay, and put 10 in here. And that result turned out to be roughly 453. And of course, these answers are theoretical. I mean, there's no reason to believe they're going to be exactly that amount, but that's what the model is producing for 10 years. So we have another point, so let's go ahead and put that down here. And let's see, we'd go over here 10 years and up at approximately 453 would take us up to about the middle between 400 and 500 roughly, and so somewhere here. Okay, so we got that. And then it says find the population after 25 years, which is the same kind of thing. We're going to do end of 25, and that's going to go ahead and have the same kind of notation as the problem above where we did 10 years, except we'll be putting 25 in for t. Okay, and the result of that calculation is going to be, let's see. Actually, I don't have that worked out already. I'll have to go ahead and do that calculation. And I'll just show you here. I'm going to use my fraction feature on the calculator and put that in there. And so I have alpha y equals. Choose my fraction feature. And let me see if I can get this all to show here. That looks good. And then I'll just put 20 and then parentheses 4 plus 3 times 25. Close that parentheses, and then down on the bottom I have 1 plus 0.05 times 25. And that answer turns out to be 702. Okay? And I would think I'm getting pretty close to my limit, but we're going to actually work the limit out here in a minute with some division. So I have 702, and we'll go ahead and plot that point also. And that would be, let's see here at 25, which would put us right here. Oops, where's that? Show you this graph here. So at 25, I would be up here at about 700 and be somewhere right around here roughly. And you can see that we're kind of growing. We're growing like this, right? Now, this will is going to reach some kind of limitation that we call a horizontal asymptote. And the way we're going to do that is through division. We're going to go ahead and it turns out that we could go ahead and manipulate our original function a little bit to put it in a better form to do the long division. Originally it looked like this, and I'm going to turn it around so I have my variable term first. And so I multiplied and I got 80 plus 60t, and then I turned it around to be 60t plus 80, and I turned the bottom around to be 0.05t plus 1. And if I do that long division, set it up like this, 0.05t plus 1 divided into 60t plus 80, it turns out that you can multiply 0.05 times 1200, or another way to say it is 0.05 divides into 60, 1200 times. So if I multiply my divisor by 1200, I would get 60t plus 1200. And when I subtract that, I would get a minus, right here, a minus 1120, which is really my remainder because I can't find a number times 0.05t that'll give me a constant. I'll get a t term. So really I have this, minus 1120 over 0.05t plus 1. And what I have here, this is really still my function, right? My function in the exact form is 1200 minus 1120 over 0.05t plus 1. It's exactly equal to the original function. But the reason why this now gives me an idea of what the horizontal asymptote is as time gets big, I'll be dividing by a really big number here, and this fraction will really kind of go away. It'll become insignificant, and it turns out I'm approaching y equals 1200 for really big values of time, and that is why what I have here is a horizontal asymptote at 1200, and I'm coming across here like this at 1200. So what's happening is my function now is coming up like this, and the fish population is, according to the model, is expected to grow, but eventually it's coming and meeting that. I mean, this isn't a perfectly straight line, by the way. There is a slight curve to this, but it is, and it depends also on how you scale this. It may look straighter if you spread the t-axis out more, but it is a curve, but it is approaching this and starting to come underneath here, and it'll never cross this. It just approaches it.